Hello, my name is Sace Park, and this is Projectile Motion Physics, Lab 2. The purpose of this lab is to use fundamental principles of physics to analyze the projectile motion of a real-world object, in our case, a duster, and compare it to the computational model. How far will the observed object deviate from the theoretical one, which is the code? So just a little preview. It is predicted that the observed will deviate from the computational that has no drag because there is air resistance in real life. The fundamental principles in this lab are Newton's second law, which is the net interaction between system and surroundings, which is the net force, to the observed motion, which is the change in momentum. From this law, we can get the position update formula, which is right here, and the velocity update formula, which is right here. And all this comes from the Newton's second law right here. And gravitational force. Gravitational force is the force of attraction that pulls objects that have mass together. This is the equation for gravitational force. Drag force is a resisting force that resists the motion of an object moving through a fluid. If there's no drag, then F drag is equal to Fg. And the equation for F drag is right here. Okay, so assumptions. Drag and gravity are accounted for in most of the graphs. There is one computation model without drag. These are the forces acting on the duster, which is the system. So for our procedure, we recorded a video of a duster, which is our system, thrown in projectile motion. Our surroundings are forces of gravity and drag. Everything else is also considered surroundings. Using Tracker, I track the X and Y position of the duster every frame. Using the code on GlowScript, I created a computational model of the duster that includes the effect of both gravity and drag. We also made the position and time graphs for both X and Y positions of the observed and computational model. Here is a picture of our tracker data and also our duster that we've thrown, and we can see a downward exponential type graph. This is the code that we use to make our computational model. The ball's mass is 0.045, ball position is right here, and ball velocity. Delta is the default 0.033. Gravity is equal to 9.8. F grav is right here. This is the equation for F grav in the code. F net is equal to F grav plus F drag. The ball velocity update formula is right here, and position update formula is right here. These are the position and time graphs for both X and Y that we got from the code. And this is a combination of both the X and Y position, which would give us the trajectory of the object. A comparison of the observed and computational. So in X versus time, we can see that the blue, which is our tracker, deviates from both the green, which is the code drag, and the dotted, which is the no drag from code. So even with the drag in the code, it still deviates. And for our Y versus time, we can also see that the tracker data, which is the light blue, deviates from the drag, which is from the code, and our dotted, which is from the code. So sources of error. Camera angle would affect the measurements. The shape of the system. Our system was not a ball, it was a rectangle. In the computation model, it was a ball. Surroundings, like friction and the presence of air from places such as the AC, can interfere with the data. And also tracking, we use our fingers to place the center of mass in the tracker. So for the terminal velocity question, there is no graph that represents the terminal velocity, as the time it takes for the duster to reach terminal velocity is long. I would have to drop an object from a high place and record it until it hits the ground. When the velocity levels off, that's the terminal velocity. Our lab, we didn't have that time or the height to reach terminal velocity. So for the what ifs, if I threw an object straight up with the same initial speed, it would take longer for the duster to be at y equals 0, or whenever it hits the ground, because the projectile in motion only has the vertical component of velocity, so v null sine theta is affecting the time in air. That's the only thing that's affecting the time in air. But if the object was thrown straight up, then the entire velocity will be used, making the time it takes longer.